So can I start? Right. So first of all, I would like to thank Arvi for inviting me. So the topic of my talk is the inverse Littlewood-Offord problem, and it is joined with Van. So let us first start with a definition. So let V be a multiset of n non-zero real numbers, and let eta I be IID Bernoulli random variables. So eta I takes value plus minus 1 with equal probability. And we introduce the random sum. S is the sum of eta I vi. I range from 1 to n. So S may be viewed as an inner product, or even the distance from a random vertex of the hypercube to a hyperplane or a random walk. And we define the concentration probability of V is the maximum probability that S is concentrated at a single point. That is concentration probability. All right. So this quantity was investigated long time ago. It was motivated by the study in random polynomials. Littlewood and Offord raised the question about the concentration probability for arbitrary V. And they proved that no matter how we choose non-zero VIs, the concentration probability is always less than 1 over root n times the factor of log, right? And the proof is the use is analytic. And very soon after, Erdos gave a refinement. So Erdos proved that indeed the concentration probability is always less than n choose n half over 2 to the n. So which this one is of order 1 over root n. And the result is optimal, and the method Erdos used is quite simple and very beautiful. So he used Spanner's theorem in chemetrics. Right? And this bound is optimal because so everyone sees that if all the VI are 1, then S has binomial distribution. So the concentration property is the middle coefficient, which is this. So the Littlewood-Offord Erdos is classic in chemetrics, which has generated a lot of research, in particular from the 60s to the 80s. So there are several ways to extend the result. So one way is to generalize the result to other groups. So for example, Kleiman considered a version where all the steps VI can be complex numbers or vectors in the norm space also. Another direction is to improve the concentration probability under additional assumptions on V. All right. So for example, Erdos and Moser in the early 60s, they showed that if all the steps are distinct, then the concentration probability is less than, in order less than 1 over n to 3/2 times the factor of log. Right? And Erdos and Moser conjectured that the log factor here is not necessary, and it was confirmed by Sarkozy and Szemeredi several years after that. So Sarkozy and Szemeredi proved that concentration probability, in case all the VI are distinct, is at most 1 over n to 3/2. Right? And this bound is sharp, which can be seen from the example, the basic example that V is the set of integers.
What did they use in their proof?
They also used Spanner's theorem. Yeah, they also used that. Oh, real numbers, yeah. They didn't know how to prove for complex number, actually. Yeah. So they...
If you have the assumption just that they are
then this is still true.
It doesn't
So-
matter because you ask about the probability that they will attain exactly some.
Just 1 point, single value. Yeah, right. That concentration property at single point. Right. So general result in this direction is due to Halasz. So Halasz in the 70s, he proved that if let n sub d is a fixed integer, n sub d be the number of 2D tuples, vi and vi prime, satisfying that the sum of the vi is equal to the sum of the vi prime, then the concentration probability is bounded from above by n sub d over n to the 2d plus 1/2. It is a very general result, and it is sharp in a way. So Halasz theorem already implies Sarkozy-Szemeredi theorem as a special case. So how to do that? We choose PPT to be 1, all right? And in case all the vi are distinct, then this equation has only n solutions, trivial solutions. Vi is equal to vi, nothing else, right?
I don't understand this statement. The number of 2D tuples.
From V.
From
From
V
V.
to the 2D,
Oh,
right?
oh, okay.
Right. Each one is from D. They can be the same.
Okay.
Yes.
So you're looking. Okay.
Right. So this equation has only n trivial solutions, right? So n sub 1 is just n. So we put it in here. We get 1 over n to the 3/2.
And what did he use in it?
What did he use? He used analytic method and some probabilities, some probability there. All right. So
Methods you mean like Fourier or what?
Fourier, yeah, exactly.
So the best case is for distinct elements?
Yeah.
Yeah, this is the best.
Okay. So this is in between all equal and all distinct. I mean, this theorem deals with the case between.
Now this theorem is a very general theorem, but if we assume that all the vi are distinct, then it implies that PV is bounded from above by 1 over n to 3/2.
Cannot be
This
small.
bound
Cannot be
is
smaller.
true for entity. You
This
can take
for every.
But can it ever be smaller than 1 over n to the 3 over 2?
Yes. Yeah, take an exponential sum, then take
Oh,
1,
exponential
2, 4, 8.
Right.
Of course, it can be smaller.
All right. So fine. Another famous result in this era is that of Stanley. So in fact, Erdos and Moser conjecture that if all the vi are distinct, then PV is in order it is less than 1 over n to the 3/2. But they asked what example gives us the optimal concentration probability when all the vi are distinct. Right. And Stanley answered that question in the 80s. So Stanley proved that the set of the symmetric set of n integers here is the one that has optimal concentration probability. All right. So this exact result, kind of, and it was one of the highlights of algebraic combinatorics at that time, at that moment. Right. And so Stanley's proof used machineries from algebraic geometry. So he used the so-called Hart-Lefschetz theorem, which is out of reach by the combinatorial community at the time, actually. Right. So there are many other variants due to Furedi-Franco, Griggs, Von, Nguyen, etc. So, for example, Furedi and Franco consider the concentration, the optimal concentration probability when all the vi are vectors has length at least 1, right? And what is the concentration probability that sum S belongs to a small ball of radius 1, something like that. And that paper was in the annals math, actually, in the annals. And for example, Griggs consider a version where all the vi, all the steps vi are in general positioned, are vectors of general positions, and the optimal the concentration property is well related to another quantity from database security. And for one would consider, for example, given a modulo Q and all the VIs are coprimes with Q, then what is the concentration probability that the sums S concentrated a class, modulo class, something like that. Yes.
Is there a simple way to see that if you replace the theorem by all the VIs are just non-zero, then the set V0 should be just...
Right. So here they ask like, just assume it, so Ederson was asked a question for just with the assumption that the VI are distinct. So there may be zero, there could be 0, 1. So.
And just, is there a simple way to see that the 1, 1, 1, 1, 1
right.
is the worst for just non-zero?
Is it a simple way? I mean the Erdos proof.
Yes.
Right. That's the simplest proof that I know. Right. Just Spanner's theorem, yeah. Which is high school, whatever. All right. So can I move on? Right. So our goal is not trying to improve the bound for concentration probability, but we are trying to find the reason why the concentration probability is large. Right. So, for example, we try to find what is the probability of it that the concentration probability is greater than n to the polynomial n. Right. And that is sort of an inverse Littlewood-Offord problem. So let us just go back to Halasz theorem. So Halasz theorem says that if the concentration property is large, then n sub d is large, right? So n sub d is sort of additive energy of the set. It measures the additive energy. So from Halasz theorem, we conclude that if PV is large, then we have large additive energy, in a sense, right? But it doesn't say much. Yes.
So I just wanted to make one comment, which is energy is often used for collision probability, or we sometimes call it collision probability of the distribution. Probability that if you sample twice from the distribution, you get the same value.
Okay.
Right, but here this sampling may be done from a convolution of the set with itself detached. So the bound holds for...
Well, the thing is the distribution is pick the elements from the
Exactly. Pick the elements and add them. Yeah. And the bound works for any D you want.
Right.
All right. So we are going to, thank you. We are going to translate that into structure for V. So it's sort of like Feynman's theorem or something. Right? Feynman inverse theorem says a set has large additive energy, then we can say something about the structure for that set. All right. So let me just so the plan is first to give some examples of V which has a large concentration probability. So he did just optional. So for a given set, then the iterated some set Ki is the set of this form.
So are you trying to go through Halasz theorem? So
No, I'm not going to.
Halasz is the reverse.
Halasz is the forward result.
But you said that if PV is large, then ND is large. So are
Right.
you trying to prove that if ND is large, then there is structure?
Right. I'm trying
go
to.
directly from PV.
No, but it just that was implied from Halasz theorem, but it wasn't implied from his method actually. But we are trying to find a way, like why our structure is reasonable or something.
It isn't the case that if ND is large, that there is a concentration, right? So there could be a large ND, and where the bound is not, where there is no element of high probability.
I think if ND is large, then you have a high.
Say again. I'm
The
sorry.
question is if it's in some sense if and only if. It will
If and
follow
only
from
if.
what is
Right.
final result that it is an if and only if.
Okay, so that's what you're trying to do.
Right. So it is true. Like if we has strong structure, then the answer D is large. That is straightforward. Yeah.
So,
We're trying to find the reverse.
Can I ask again? So, are you trying to show that if PV is large and there is structure, or that
There's structure, yes.
Okay, but are you going to show that you assume that ND is large? Are you going to use Halasz theorem?
No, I'm not going to use Halasz theorem. Yeah. All right. So for set A, then K is that. All right. So our first example is so pick a interval of integers from a negative m to m, and assume that all the vi's are integer from this interval. Then the sum belongs to a little bit longer interval from negative nm to nm. So the concentration probability by pigeonhole principle is at least 1 over nm, right? So which means that if this interval is short, then and all the vi's belong to this interval, then the concentration probability is at least 1 over n. But in fact, we can do a little bit more, that with high probability, then our random walk will stop in a smaller interval, right? And so in this case, the true concentration probability is 1 over root nm, right? And it is kind of best possible.
High probability is over the choice of v1 to vn from
No. V1 to Vn
Are fixed.
Stereo,
Yes,
just SIs.
Right. Yeah. Okay. So here people know all about GIP. So GIP is the set of this form. Di are generators. Li are the dimensions. Right. If all the possible sums are distinct, then Q is proper answer. So just keep this part right. Everyone knows.
No, don't hurry. People don't know everything about it. Don't hurry. You can say what's on the slide.
All right. So a geometric generalized arithmetic progression is the set of this form. So each element can be written in the sum as a sum of x1 d1 plus up to xr dr. R is the rank of the GIP, right? All the di's are generators, and xi are integers, vary from negative li to li, where li are the dimensions, etc. Right. So it is kind of a map from a box to the setup to the abelian groups.
Yeah, so the special cases where R equals 1, and then we have a normal arithmetic.
Right. Yes. When R is 1, the rank is 1, then we have the usual.
Yeah, a normal arithmetic progression would also allow to add in 1, so R could be 2, but Li.
You mean the shift? Yeah, there's no like this is like homogeneous.
This is called symmetric. So if you don't want symmetric, then you put an additional element there.
Yeah.
We are working with symmetric GAP actually. Yeah.
Then you could also just make the first Li. Okay. If you make it symmetric, then there's no way to have it just be 1.
All right.
Sorry.
So this
wouldn't
symmetric.
matter for the I mean, for the bound, you can symmetrize without.
Right.
without
There's a
generality, so it might as well be symmetric.
yeah, which is this nice object somehow. All right. So our next example is we pick a symmetric GIP, and we assume that all the VI's belong to this GIP. All right. Let's see. So, yes. So
All the VI's, sorry.
all the VI's are elements of this GIP. So, we're
Okay. I see. Okay.
Right.
Like before, we picked them from an interval, which is an arithmetic progression of
Right.
dimension 1. Now we're picking
Right.
them from an
Exactly.
arithmetic progression of dimension
right,
R.
a general example. Right, thank you. So we pick a GIP, a general GIP, and we assume that all the VI belong to this GIP. Then the concentration probability is at least 1 over the size of NQ. right? So which is at least 1 over n to the r times q. At most, which is at most.
Square root, right?
Right, and then, but again, with high probability, the random sum will be concentrated in a smaller box, smaller GIP. So in this case, the true concentration probability is 1 over n to the r half times the size of q, right? And this is sort of best possible.
So we should think of R as constant.
R is a constant.
The n going to infinity.
Right.
The allies are not necessarily constant. They may be.
Right. Right.
The allies, yeah.
The dimensions can depend on n, but R is a fixed, like the rank of the GIP.
So Q is proper.
Q is proper, or even not
It
proper.
doesn't
It's
matter
fine.
here.
Yeah.
Yeah, you just get the unit, it's even bigger.
All right. So what we have shown is, seems like, if our set, if all the VI belongs to a GIP of small cardinality, then the concentration probability is large. Right. So there's a theorem, whatever. Okay. So there's a beautiful theorem by Tao and Vu a couple of years ago. They proved that if the concentration probability is at least 1 over n to the c, then there exists a symmetric proper GIP which contains almost all elements of V, and this GIP has bounded rank and it has bounded cardinality. So the cardinality Q is polynomial in n at most, right? So which is kind of a inverse theorem.
Do you want R to be small or large?
R is small. R is bounded. It's a constant.
That's
Right.
the only explanation for high probability is if it's a GIP. That's the only possible explanation.
So this characterizes polynomially bounded
Right.
probability, but
Not for
n to the
exponential.
negative c for any particular c.
Right, right. So supx exponential, it doesn't work. This method doesn't work for that. So there are just one comment, remarks. So the presence of small set. So we cannot. So the presence of small set of exceptional elements is not completely avoidable. So we can just add arbitrary like little log n elements in V without any effect much, right? And to the little of 1. So so we cannot avoid that, right? And our main focus will be on the rank and on the size of our GAP instead. So how big can a GAP be? So we want it to be as small as possible, right? And so in the weak inverse Littlewood-Offord, the cardinality, the C prime is implicitly, it depends on epsilon and C, which is not what we really want. So
And here epsilon is just
to
say
make
what
to
the little
right.
means.
Yeah, epsilon for any given epsilon. Okay, so
you want to say why they were motivated? Do you want to talk about random
I will-
matrices, or-
I will-
yeah,
I will-
okay, good.
some
That's
applications
all.
of-
Okay,
yeah.
great. Yeah.
So about 2 years ago, so Tao and Vu sharpened the result to obtain an almost best possible bound. So again, assume that the concentration probability is large, then most of the elements of V can be contained in a GAP of bounded rank and now of cardinality n to the C minus R half time plus epsilon. So C prime in our case now is kind of explicit already, and it is sort of best possible with so except the n to the epsilon factor here, right? Yes.
Is it clear that should be a dependency in both of them on epsilon?
Oh, wait, let's see.
Say again, I'm sorry.
No, you asked whether there is a dependence on epsilon, so you just wait and you'll see what.
Which depends on epsilon. This
The
part.
R, whether
Both
R
of them
has to
depend,
This-
So one of them should depend on
Right. If R depends on epsilon, then this one is also depends on epsilon.
But R can't be too big because then this,
Right.
the cardinality would disappear.
R is always less than C, 2C or something. 2C minus plus 1. Yes. And it can be make smaller if we put epsilon to be larger. All right. So let me just, so that the technique they used is Fourier analysis and theory of random walks and replacement principle. So let me just give some applications of this theorem. Right. So the first application is use inverse theorem to deduce forward theorems, right? So for example, we can show that using the result, if all the VI are distinct, then the concentration property is for the 1 to the 1 over n to the 3/2. The Sarkozy-Szemeredi theorem, as asymptotic version, right? So we can use Tao and Vu's theorem. So how to do that? So first we assume that set epsilon to be small enough, depending on delta, and by the inverse theorem, most of the VI are contained in a GAP of rank R, so forget this for the moment, and the cardinality n to the C minus R half plus epsilon, if you remember. And so C is 3/2 in our case, he's R half. He's the actually C is 3/2 minus delta actually, sorry. So R in our case must be 1. There's no other case. Because if R is 2, then this bound is about order root n, which is impossible because Q contains most of the elements of A. So the size of Q must be at least n in order. But if R is 1, then we can still obtain contradiction because in that case, the size of Q is also little little, right? So that's contradiction. So this assumption is, so BV is always less than this. It makes sense? Right, so to prove that, first we assume that PV has large concentration property, but that large concentration property would give us a contradiction. Right. And another applications I won't have time to talk about, but very important application is to use a version of it to establish the circular law conjecture for random Bernoulli matrices. So the circular conjecture, it was made a long time ago in the 50s. Like, is it true that the eigenvalues of a normalized random Bernoulli matrices is equidistributed in the circle, the unit circle or not? It was verified for normal distribution, but for the Bernoulli distribution, and it was an open question. So how to use the theorem to establish this? So at some step of the argument, they want to estimate the number of VIs of VIs which has large concentration probability, right? So because of the inverse theorem, large concentration probability, if a set has large concentration probability, then it has a structure. So to count the number of such sets, you just need to control the structures.
The elements are vectors, really, right? I mean,
they are complex numbers in the VI are complex numbers. Yeah. So yeah, the set V now is a vectors, right?
vectors, yeah.
Right.
They are looking at eigenvectors.
Exactly. Right.
Random matrix.
Right. So to control the number of those V's, so in order to count the number of those V's, they just count the structures, right? And the structure is helpful in a way. And the version they used is a little bit different from this. So it's not for the concentration probability, but it's for the small ball probability. I will talk about it later, a continuous version of it. And the theorem is not as neat as we have. So here's the main result. We are able, first, the method Tao and Vu used, first of all, the result is not, it is sharp, sorry. But there's a factor n to the epsilon here. We need to so there's still an n to the epsilon factor here we need to think on. Another thing is the method they used. It is elementary, but it is very hard to adapt. It is very hard to follow this approach to the continuous case. So in their paper, it took about like 20 pages to prove a similar result for continuous setting.
So continuous is with instead of plus minus 1, you have a Gaussian?
That's one also, and instead of concentration probability, we consider the probability that the sum is concentrated in a small interval instead, not at a point, but in a continuous interval. Yeah. So the method and the result are the two things that. So we are able to remove the n to the epsilon factor, right, by a different approach, totally different approach, and we are also able to adapt our result to the continuous setting easily, right? So here's the main result in the concentration probability setting. So if PV is greater than n to the negative c, then most of the elements of V are contained in the GAP of bounded rank and a small size and as small as we expect. There's no loss anymore. So the tools we use is just elementary Fourier analysis and Feynman's inverse theorem. So we directly use Feynman's inverse theorem in our proof, which wasn't used in Tao Vu's proof. All right. So the first application is we can now deduce all the forward results mentioned about without any loss anymore. So not asymptotic, but it's a bright order. Even we can deduce Halasz theorem from our result, right? Because it gives us a very strong structure, as strong as we expect. So from the structure, it is easy to compute the number of the additive energy. And
the additive energy of a GAP you can calculate already.
We cannot.
You can calculate.
We can calculate that. And let me just recall. So we can also sharpen our result to obtain an exact result, like that of Stanley. So just recall the result of Stanley is this. Then we are able to prove first. So Vi and our distant elements of a torsion-free group. So any torsion-free groups works equally well. All right. So if all the Vi are distant elements of a torsion group, then the concentration probability is at most 1 plus little 1 times the what? So it means that this one is asymptotically the optimal. The one has optimal concentration probability, and another one is about the stability of the maximizer, the stable this one is a stable maximizer, which means that if V is a set which has concentration probability which is close to the optimal one, then the set has the set V must be close to the optimal one. In a sense, right? It's kind of stability, and I do believe that we cannot prove such a result from an algebraic method. Okay. So I would spend several minutes to talk about how to.
You have at least 20 minutes. So
right. Thanks. So let me just give a sketch of this, how to use our theorem to prove such a thing. So first we assume that PV is the set concentration probability at least delta times n to the negative 3/2, where delta is very small, right? So up the right order. By our theorem, we can deduce easily that then most of the elements of V belong to a very short interval after dilation. Right, 99% of the elements of V belong to a very short interval. And we now use a formula for concentration probability. So let me just write the formula. So we need to consider the event that S is equal to some U, right? So this can be written as integral from 0 to 1 of exp 2 pi I S minus U x dx, right? So the probability of this guy is just the expectation of this one, right? When I take expectation, because they are independent, so 0 to 1 is xp of 2 pi I, the notation, eta j vj x, product of this from 1 to n, and it's xp 2 pi I du x, something like this dx. All right. And the expectation of that, because eta I takes value plus minus 1, so the expectation is just cosine, right? So that's the formula, analytical formula for the concentration probability. Okay. And now we just use the strong structure on the VIs to compute, to give a, so normally we cannot give a formula for this concentration probability. But once we know that there are, we know that there are most of them, we know the strong structure of that set, so we can give a asymptotic formula for the concentration probability, right? So this formula says two things. So assume that V is a set of integers, that among those V is a set of integers, then the one that has least variance, least sum of Vi square is the one that has largest concentration probability. So that explains why we took the set of symmetric sets from negative n half to n half. And it also says allows us to deduce the stability theorem.
What is irreducible?
I mean, there's no common no, there's no common divisor. Right. So let me just give some remark. So in our theorem, the assumption of Bernoulli random variance is not so necessary. So we can take any IID, any distribution which has the property that the expectation here is bounded by something like this. All right. So they are not necessarily comes from the same distribution. It just independent, and each distribution has this property. And for example, the lazy random walks has this property. So the lazy random walks is the one that that takes value plus minus 1 and also 0. Right. And another remark is our method can be extended easily to deal with the continuous testing, the one I talked before. So for a general distribution, assume that eta is IID copies of that, not necessarily Bernoulli. Then the small probability is the probability that this sum is concentrated in a small ball, right, rather than at a point. That's the continuous version. And that is so result on this would have more application rather than the concentration probability. So very roughly speaking, it is hard to state. So roughly speaking, if the small probability is large, then we can prove that V is close to GAP close to the GAP of bounded rank and a small cardinality. All right.
So close meaning continuously.
So you have a
Just change.
you have a set GAP at so each VI must be close to one of the elements of the GAP in coordinates.
Close in norm.
In norm, in the L2 norm, for example. Right. It is hard to state, and we don't have an optimal version for this.
The other direction, if it's close to GAP, then the ball probabilities are large.
If we assume something else on the parameters of the GAP, yeah. If the GAP, so it has generators, and if the norm of the generators are small, so yes. So even the forward result is not so clear. Right. So in the rest, I would like to give a sketch of our proof, which is simple in a way. So it has two steps. The first step is to translate that from the large concentration property. It means that there's a set which captures most of the elements of V such that it has polynomial growth.
So
This is
integer times a set means adding it to itself this many times.
right. So yeah. Yes. Any question? And it seems to me that is a strong statement actually. So here each VI just is involved just once in the sum, but then here we might say in this sum it is involved root n of times. Yeah. I don't know. Right. And the second step is we use Feynman's theorem to prove that if a set V prime has this growth, then that set must be contained in a GAP also. Right.
So this is different than our usual applications of Feynman or some product.
It is
because
different.
It's not a constant number of
Exactly.
times that you are adding the set
Right.
to itself.
It is very strong, right? You're adding it
It is strong.
square root n times, and it grows only by a constant in the exponent.
Yeah, the assumption is strong, but it's not the standard assumption.
Right. So let me just talk about the second step for a bit. All right. So here's the Feynman's inverse.
Actually,
It is.
because imagine that in the Feynman you add a plus a, so it is less than a constant times a. Add again.
Yes.
A plus a
Yeah,
plus
so
a.
you can infer that some set,
Immediately,
some
you
but some,
immediately
yeah.
get, and there is a point where it would
It
double.
would, yeah, the
then-
doubling
then-
would be
then
small.
it will not grow too much because the bound is n to the c, and if you imagine then you have n numbers and add them, then even the largest sum will be less than n to the c.
Yeah, so
and
the
square
inference is
actually.
about.
So therefore there is a place where you don't have the jump and then you use Feynman.
I understand, but it's not clear how to. Yeah, so that's.
All right.
But it's a different set, and also it's not clear how the value of c. The value of the exponent c has to be critical here. I mean, they use it
Right,
for the
but-
size of the
True, but in
arithmetic.
Feynman there is this then whatever is the double constant and then the dimension of the of this.
Oh, it's tight enough for this. Okay.
Right. So, okay. In order to prove that theorem, we use some sense stronger than Feynman's inverse theorem. Okay. So he just recalled you Feynman's theorem. So without so if a set has a small doubling constant, then there's a proper symmetric GAP that contains that set. All right. So of course we don't in our theory we don't care about how is it depend on C or so. All right. So we try to use this theorem to prove some in some sense a little bit stronger. So assume that V prime is a subset such that chi V prime is less than chi to the I times V prime. Chi is any number. Right? Then V prime can be contained in a proper GAP, a bounded rank, and a small cardinality, chi to the I times V prime, which is the bound here over chi to the R. So in a sense, so if we set k to be 2, then it is Feynman's theorem in some sense, right?
So is there like a polynomial Feynman theorem, or is
It
it
is.
conjecture, or it's not?
No, it's not. We don't talk about the implicit dependencies. Yeah. All right. So okay, so we call it long-range inverse theorem, and we just use Feynman's theorem to prove this.
You prove in the same way.
Yeah.
as
So the method, that method is due to was first introduced by Tao by Szemeredi and Vu. So to prove that theorem, just very in one slide to explain. So we consider the set sequence. We're trying to prove this theorem. Sorry, this theorem. All right. So we just make we consider the set sequences a sequence v1 up to vm, where m is of order log k, where vi plus 1 is vi plus vi, right? And let's see with the constant. So v sub m is, so c is the constant such that c to the m is v sub, the ratio between the last one and the first one, right? And because of definition, there will be an index where the ratio is less than c, all right? And so we then apply Feynman's theorem for this set in the middle, all right? And then after modulo some combinatorics, we from here, so here's our starting point. So after modulo some combinatorics, we can prove our long-range Feynman's theorem, the long-range inverse theorem. All right. And the rest, that's the second step. For the first step is a little bit technical, so hopefully I have 10 minutes left. So for the first step, let's just recall the first step of the argument is we want to deduce that if a set has large concentration probability, then there's a set V prime which contains a multiple element of V which has this property, right? So
Do you need the square root n there, or is
Yeah,
it
because you want to get R over 2 in the exponent of
right,
the
exactly.
theorem.
Root
It's
n to
very
the k,
this step is tight in itself?
right?
It's,
Right. We really need that. So the first step in that. So first we use the trick like to embed V into a very big Z mod PZ group, right? To use in order to use discrete Fourier transform. So this concentration property. So PV, the concentration property in the so in Z mod PZ, it is bounded from above by this. Right? Just using the same identity, right? So if the concentration property is greater than that, then this one is greater than n to the negative c. Okay, and we use property of cosine. So this is bounded by the sum of exponential sum of exponent of this in the exponent. All right. So because we just estimate these guys separately and we just add them together. Okay, so that's just it. Now the next step is we define the level sets. The level set S sub k is the one where in the exponents this sum is less than k. And so basically, if k is greater than log n, then the contribution when psi in the S sub k is negligible. Because if it's greater than log n, then this one is very smaller than 1 over n to the c. But it is negligible. So what we need to pay attention is just for those k which is of order log n. Right? So just basically there will be a level set which is of order p over n to the c. Of course, there's always some constant depending on some number depending on m here, but let me just assume for now that.
So P will be much larger than N, I
P must
be
P is very huge.
Yeah,
Right.
it would just be some large.
Right. Very large. All right. Then
So what? There are many Fourier coefficients where the sum.
so
The sum of squares.
yeah. So
Can you explain this line for again?
This line? right. Sorry. This one is the norm. This norm is the distance. The distance from this one to the nearest integer. Right. So
Okay.
the cosine.
Oh, for the norm, the square of
Yes.
the norm is not the square.
So the cosine of x is less than sp of whatever a constant c here times the number of x squared or something. That is I want to use that.
So this notation of the norm is again
The distance from x to the nearest integer.
okay, and the first inequality.
The first inequality here is this one is n to the c this one, right? And the concentration property by that formula in z mod pz, if we take absolute value, then the cosine is absolute value cosine, and the absolute value of this one is just 1, right? So that's an upper bound for the concentration probability, right? Product of cosine. And then I even apply an estimate for cosine to get this. Okay. Yes?
So this is the probability that the sum is actually 0. This is a, okay.
So when
equal to u just adds a constant, just adds another phase to the probability when you calculate in the exponential.
right. Okay. So here's the levels. So once again, this step is fine, right? So there will be an m of order log at most log n, which has large cardinality, p over n to the c.
Why is it not? Oh, just because it's in the exponential. Okay.
Right, in exponential, right. Just briefly. So the next step is I want to say that, in a sense, that it means that all the elements of Vi are orthogonal to this set as well. Right, because this sum is small. So on average, this sum is about n half. Right. But here, this sum is less than log n. So it means that our set V is strongly orthogonal to the set level set Sk. So it is strongly enough such that I don't know. It is strong in a sense that if we add the elements of Vi together, the resulted set is also orthogonal to the set the level set. So mathematically, so we sum. So sorry. Here is the definition, right? S sub m is the collection of all the psi such that the sum of these squares is less than m, right? In the next step, if I sum over psi in that level set, I get this estimate, right? Which is some, and in the next step, we set epsilon to be, we choose epsilon well, for any given epsilon. From this inequality, we deduce that there will be at least 1 minus epsilon times n elements which has this property. Otherwise, we run into contradiction, because if this guy is greater than that guy, and we sum over Vi, then we get a contradiction, right? So what does this mean? This sum square is less than 1 m over n times the current root of Sm. This is strong enough that we if we consider the set chi v prime, where each element is the sum of this, then this sum, where u is in chi v prime, this sum is less than Sm over 2. Sm over 2 is the average. If we take u to be a random number, then the expectation of this is Sm over 2, right? But now, if any u in this set, then this sum is is less than Sm over 2, using Cauchy's rod and the definition of Sm. So basically, and now we consider the set of those U such that the sum here is less than Sm over 2. Then by Parseval's identity, so by Parseval's identity, the set of this U is less than P over Sm. So U now is sort of orthogonal to the set Sm. And chi v prime belongs to U. So the size of chi v prime is less than P over Sm, which is less than n to the C. Right? So I don't know what to. So that's the end of the step number 1. So we have just shown that V prime is orthogonal to the level set in such a way that this set is also orthogonal to that set in a sense. And then
V prime was just obtained by averaging, right? V prime was just obtained by averaging.
Right, by averaging. That's the only step that we lost some elements from V. Right. And so V chi V prime is less than n to the C, the size of that. So that's what we expect. So it's a little bit technical.
K is about 2 times. It's not exactly. You may lose a log or something like this.
We gain. We will.
K is something like n over.
But in the estimate, we will gain something. In we will gain actually if m is. So here, for example, we may have some extra factor here for m.
I see, so you don't lose.
Right. We don't lose, we gain.
So the worst case is where m is a constant.
Right, exactly, the worst case. Okay, so I just would like to stop. Thank you very much.
Questions?
Yes.
So, as far as I can tell, this isn't still isn't an infant only if, because you could contain a big, you have 1 minus epsilon of your elements.
Right,
but
exactly.
there's still many.
Right.
Your probability of all your elements falling from that
right.
into the.
So that's
that. Many elements outside that, so that are.
Exactly. So that's one of the effect of our result. But in the case that if the concentration property has order n to the negative 3/2, then we can prove that all except a constant number of the elements. So have to be out. So we can.
One-dimensional. It would be just a one-dimensional.
One-dimension case, just one-dimension case. So in that case, we can prove such if and only if argument. But in general, we don't. Yeah. Right.
Is there something you could do for non-abelian groups? Instead of plus minus 1, you could look at the words.
Right.
Like a random word in a group.
So we're trying to think on that, but no result so far. So.
Okay, thanks a lot.
Thank you.